So now we're going to talk about acid-base reactions. Acids, we first have to clarify what acids and bases are. Acids will be any type of solution, right? Because it's in water, it's an aqueous solution that produces H plus ions and whatever other anion was there, right? Because acids will have hydrogen. You'll start to notice they have hydrogen, and then they have a polyatomic ion or a halogen after it. When they are in an aqueous solution, they will ionize, and they will increase the amount of H plus ions in solution and whatever polyatomic ion or ion is after it. A base, essentially, it's what we call the opposite. So bases have hydroxide ions in them, and they increase the amount of hydroxide ions in solution. Now, another way that you can represent acids or like acids in solution is that they increase the amount of hydronium ion. And the reason this happens is because that H plus joins with water, and then you end up getting H3O, and it actually has a positive charge. When we have acids and bases reacting together, so for example, nitric acid and calcium hydroxide base, what you end up getting is a salt and water. And this is called a neutralization reaction. So in the lab, if you should never drink acid, and like in a beaker or something, you neutralize acid with base, but in your body, no, that would not work. The net ionic equation, so now we know what net ionic equation is from our learning about precipitation reactions, is always going to be H plus OH gives you water. So anytime I ask you what is the net ionic reaction for a strong acid and a strong base, this is what you're going to tell me. H plus and OH gives me water. So these are our strong acids and bases. Anything not on here, so these are strong acids, right? These are strong bases. Any type of other acid or base not on this list are weak. So anything not on here on this list is weak, whether it be an acid or a base. They do list some weak acids and bases, but otherwise everything else will be weak. So we mentioned what a acid-base reaction is called, a neutralization reaction, but there is something we can do called the titration that actually allows us to determine certain values, specifically molarity of, let's say, an unknown acid, right? An unknown concentration of an acid. So in these acid-base titrations, you'll have an acid, right? We do not know the molarity of it. So what you do is you have something called a burette. This is our burette. You have it filled with a base, right? It has OH of a known concentration. So this is your known, this is your unknown, just like in all the problems that we solve. So you keep adding until you get to a certain point, which will be indicated by something called an indicator. So once you reach the same amount of moles between your acid and your base, you have something called the equivalence point. So you'll keep adding, it'll flash pink as you're adding. You see that base dripping in there. You'll keep adding, you'll see some flashes of pink, so it's getting closer and closer to the equivalence point. And finally, when you reach that pink, that means that you have reached the equivalence point. So here, this shows you, and the indicator here is something called phenolphthalein, but actually the equivalence point for phenolphthalein is a very light pink. It's closer to that type of really baby light pink. This is actually you overshot the base, so it's like past the equivalence point. So now you did the experiment, and now you need to do essentially the math to figure out what that concentration of your acid is. So we had a known, remember, I'm just bringing this up again. We had a known, which is our molarity of our base, but we do not know our molarity of our acid, right? So we need to do the math with the data that we gathered to find the molarity of our acid. And we actually do some stoichiometry with this. So first we're going to check if this is balanced. And I'm not going to go through it, but when you go through that process, it actually already is balanced. So you don't have to worry about this one. But that should always be your first instinct. Now, let's see what data we have. So we have our volume of our base and we have our molarity of our base. Remember our mole map, which is volume, we can get to moles using a molarity, right? So our first job is to determine how many moles of NaOH we have. And remember, you stop adding base whenever it turns pink, right? Our indicator turns pink. The endpoint will occur when you have an equal amount of moles of acid and base. So the equivalence point or endpoint will happen when you have equal, so mole of base equals mole of acid. So we need to find the amount of base, and then we need to use this equation, and we need to convert to moles of acid. So that's our job. We need to go from, so this is volume of base. We're going to use the molarity of the base to get 2 moles of base, and then we will get 2 mole of acid using the stoichiometric factor. The stoichiometric factor in this case is this 1-to-1. So 1 mole of HCl reacts with 1 mole of NaOH. So let's go ahead and just follow that process. So we're starting off with ml. We actually need to convert that, so I'm going to do that off to the side right here. 35.23 ml. 1 ml is 10 to the negative third liter. So then we end up getting 2, 3, right? 1, 2, 3, yeah. All right. So now we can start. And this is NaOH. Remember, always label. Now, so we got the volume. We're going to use the molarity to get 2 moles of base. So the molarity is 0.250. Remember, with any molarity that you have, as soon as you see it and you know you need to use it, just break it up. So this means 1 liter over 0.25 mole of whatever it is over 1 liter of solution. This is solution. So 1 liter of NaOH solution has 0.250 mole of NaOH. All right, so now we're at moles of NaOH. Now we are going to use the stoichiometric factor, which is right here, to get to moles of acid. So 1 mole NaOH, 1 mole HCl. And then we get moles of acid. So I end up getting 8.81 to 25 times 10 to the negative third mole. Okay, so from here, we're trying to get molarity of HCl, right? We have moles of HCl. We also have the volume of our HCl. So essentially, we're pretty much ready. Remember that molarity equals moles over volume. And I'm just going to do this very quickly, but essentially this, you can do it on your own. But 50 ml, I'm going to convert it, and it's 0.05. Just to keep those sig figs, let's see, 3 liters. So I'm going to write the answer up here. But essentially what we get is 0.05, 0.17625 molar. Now, our limiting, let's see, this one had 3 sig figs, this one had 4. 4, obviously 3 is going to determine how many sig figs, so it's going to be 0.176 molar HCl. So that's how you determine the molarity of an unknown concentration acid using information from a titration that you completed.